we start our Chem 152 semester with Chapter 12, labeled Kinetics. In this chapter, we talk about rates or speeds of reactions. In this opening image for the chapter, we see a picture of a lizard, and the lizard is using temperature as a way to help control metabolism. So as temperatures and its body warms up, the metabolism of the lizard will also speed up. Each of the chapters that I'll be presenting will have a slide like this one. I'm using open source materials, and so this is my general note of citation of sources. So we begin our kinetics chapter by talking about reaction rates and factors that can affect the rate of a reaction. So again, kinetics is specifically discussing or determining how fast or slow a reaction will be and how we can measure those rates. An example of a very fast reaction would be sodium metal in water, or a very slow reaction would be the rusting of iron. I always ask my students, why do you need to study kinetics? And there are a couple of different reasons. The primary one, most of you taking this course are going into a pre-health field of some sort. And so for two reasons, you need to be able to determine how fast or slow a reaction is going to happen, specifically with relation to medication. In commercials, you've probably heard about time release capsules. And so we need to study how quickly or slowly medication will be released into a system. And we do that by studying the speeds of reactions, the materials that are designed to help release those medications. Understanding reaction mechanisms. For anybody going on to take organic chemistry, that course focuses specifically on mechanisms, which is an understanding of the step-by-step process by which a reaction happens. If you're studying more from the biology side of things, as our example with the lizard, metabolism is dictated largely by chemical kinetics. So if we can understand the chemical reactions happening, we can understand how we can affect metabolism. Our definition of reaction rates, again, rate is the same thing as speed. And so for reactions, we can measure rate by looking at the change in amount of substance per unit of time. Our calculation for the rate of reaction is proportional to how many collisions between molecules happen per time. Now, I say proportional to because we can't actually measure or count how many collisions happen per time. So when we get into our actual calculation, we will be looking at the change in amount of a substance over a given time. The factors that we can change in lab that will alter the rate of a reaction, concentration is a key one. Quick side note here. The main unit of concentration that we use is molarity, the capital M. And remember that that breaks down in units of moles per liter. As we go through this semester, it's going to be very important to remember the distinction between these units, molarity versus moles. And so if we think about rates from the collision perspective, it would make sense that if we increase concentration, we're increasing how many moles of a solute we have in solution. More moles of solute means more collisions, means a faster rate. Temperature is another important factor. We are familiar with the fact that as we raise temperature, we're raising kinetic energy, the movement of the molecules themselves. More movement, more kinetic energy, more collisions, a faster rate. Catalyst, you've likely heard the definition that it literally speeds up a reaction. And so adding a catalyst will help speed up the reaction. By the end of this chapter, we'll discuss how a catalyst does this. And then increasing the surface area of a solid or a liquid. If you think about a liquid evaporating, if I have a large cup of water sitting out on a counter, it will eventually evaporate, but there's not a lot of surface area there. If I clumsily were to spill that cup of water across the countertop, now that liquid is spread out over a larger surface area. Now all of those surface molecules of water can evaporate much faster. The same idea would happen with a solid in a chemical reaction. So we start by describing how we can calculate the rates of substances. If we take this pretend reaction A converted into B, our image is shown here at the bottom. We have pure A, our purple atoms starting, and at the very end, we have just our pure product B, green atoms. Notice as this reaction proceeds, the amount of A decreases. So reactants always decrease in amounts, whereas products always increase in amounts as a reaction happens. Our calculation to determine the rate of a substance is by a change in concentration. So remember, our delta symbol always means change. And anytime we're calculating that change, we're always going to take the final minus the initial. Our square brackets here are specifically referring to the concentration of a substance. Concentration, remember, we are measuring in molarity. And so for the rate of A, we calculate the change in concentration, the final molarity minus the initial, and then the same for our difference in time. Now notice for our rate calculation for a reactant, we assign this equation as a negative. And that's because, again, remember, reactants are always decreasing over time. And so the initial quantity is going to be larger than the final, which means when I do this subtraction, I'm going to get a negative value. But if I define my equation with a negative, I'm going to get a positive overall value for rate. And so the net result is anytime we calculate rate, we must get a positive value. Similar analogy, in your car, your speedometer is recording miles per hour. Right? Speed is always a positive quantity. Same idea for rates of substances. We always have to have a positive rate value. Now we can do the same setup for our product. Product B, we can calculate the rate of this substance over time, change in concentration of B over change in time. Again, final minus initial, and then time final minus initial. Because this is a product, the final molarity is going to be larger. And so for this one, we don't need to assign a specific sign for it because I'm automatically going to end up with a positive value for this one. Now, if I wanted to graph this over time, and in Chem 152, we love graphs, by the way, my reaction graph would look something like this. So I have time on the x-axis, and either number of molecules or concentration, some measure of amount on the y-axis. My reactant A is the purple slope, and that's because reactants always start with some initial value at time 0 and will decrease over time. My products will always start at 0 because I don't have any products initially, and they will always increase over time. And now the curves that we're showing here are showing what we call an average rate. So if I look at 2 dots on these graphs, when I plug those values into the equation on the previous screen, I'm calculating an average rate over a given time period. Using a real chemical example, we have the decomposition of hydrogen peroxide. In our data table down here, we are given time increments and the concentration of hydrogen peroxide over time. We want to calculate the rate of disappearance of hydrogen peroxide for each time interval. And so again, remember, hydrogen peroxide is a reactant. We define this with a negative quantity so that we get a positive rate overall. And again, our setup is going to be final minus initial and time final minus time initial on the bottom. So I'm going to do the first set here between 0 and 6 hours. For our setup, our final concentration is the 0.500 molar. Our initial concentration is the 1.000 molar. My final time is the 6.0 hours, and my initial is the 0. Now, two things to note here. One is sig figs. So remember, we have two steps here. We're subtracting in the top, which means we go by least decimal places. And then we take that answer divided by our denominator. So division, we're going by least sig figs. So again, with the two steps, we have to pay attention to sig figs at each one. The end result is that we will report our answer to 3 sig figs. And so our final answer for this one will go to 0.0833. There's our 3 sig figs. And now units. Realize that when we subtract the numerator, we have molarity. When we subtract the denominator, we have hours. And so our units here will be molarity per hour. Quick note for you, most reactions that we study are going to be listed per seconds in the bottom. We generally study faster reactions. But the general note is that for our units here, we're going to have molarity per time. And remember that any unit that's in the denominator, we can write that unit to the -1 power. So molarity times time to the -1. In this case, molarity times hours to the -1. I encourage you to pause the video here and practice calculating the rate of disappearance for the other time intervals and predict whether you think that should remain the same, increase, or decrease over time. So go ahead and pause the video, practice calculating the rest of these. All right, hopefully you paused the video to practice calculating the rest of the time intervals. And if you did, you should have gotten these answers. So key thing to note is that our rate is slowly decreasing over time. And that should make sense because of the nature of how our substances were changing over time. Notice that the slope of our tangent decreases over time. And so rates of substances, rates of reactions will change over time.